And I hope everybody had a good weekend.
Yep.
Good. I don't know. I've got a lot of, okay, I think we left off with this one. 5.3, 22/12. 5.3, 22/12. I can't remember. I think we left off here. Let's see. For a parallel structure of identical components, the system can succeed if at least one of the components succeeds. Assume, this is not a test question, assume that components fail independently of each other and that each component has a 0.11 probability of failure. So each one has a 0.11. I'm writing down.
Hubert, I have a quick question.
Yeah.
So did you say that we went over 5.5 questions?
No, we went over 5.5.
Because I was looking at the 5.5 questions and it has to do with like finding the value of factorial, and
Yeah, we
I
didn't go
at least
over 5.5.
No.
not to my knowledge, no sir.
Okay, what's the last section we went over? Multiplicative. Okay, we need to go over 5.5. All right. For a parallel structure of identical components, the probability of failure is equal to 0.11. So what I tell you, the first thing you do, write down the complement. Therefore, the probability of, and we'll write it in red since black and red are opposites of each other. What's the probability of success? 0.89. Okay, so you're going to use these two numbers because they don't give you any of the numbers. If you look for a parallel structure, I don't understand what the hell that is. The system can succeed if at least one of the components succeeds. Assume that components fail independently of each other and that each component has a 0.11 probability of failure. Complete parts A through C. Would it be unusual to observe one component fail? Well, what is one component failure? Got it written down right here. One component failure is 0.11, right?
Yes, sir.
0.11 and 0.5. Yes. Now, what am I talking about? Well, I'm going to go show you something. And I don't know if I've shown y'all this before. I don't think I have.
Are you referring to the like nickel rule?
Yeah, the nickel rule. Did we go over that?
Yes, sir, we did.
Okay. Well, I'm going to go over it again just in case, right quick.
All right, sounds good.
The nickel rule is basically 5%, which is 2.5 and 2.5. 5% is unusual.
I had a question about that.
On the test?
Uh-huh.
I told you you would.
Yeah.
Unusual. You should have got the other one, but we're not going to talk about that. Unusual, okay? 5%. So anything greater than 5% is going to fall into the green area. Because this is the pink area is 5%. It's like putting water in a bucket. If you've got a 5-gallon bucket and you put 10 gallons of water in it, what's going to happen? It's going to overflow, right? So if you get a number greater than 5%, it's going to go into greater than 0.05. It's going to trickle over from here into there. So if you have a number that's greater than 0.05, it's going to fall into the green area, which means not unusual, normal. But of course, they do everything difficult, which is called not unusual. Okay, so that's the nickel rule. So back to our question, is 11 cents greater than a nickel? Yes.
Yes.
So therefore, not unusual. All right, so that first question, would it be unusual to observe one component fail? No, it would not be unusual. Two components. Well, that would be 0.11 raised to the what? Second power, Hubert. Well, let's take out our handy dandy calculator and do 0.11 raised to the second power. 0.0121. Would it be unusual? Well, is 0.01 greater or less than 0.05? It's less than, so it would be unusual. Okay, so that's the answer to that question. So it would not be unusual to observe one component fail, since the probability that one component fail, 0.11, is greater than 0.05. It would be unusual to observe two components fail, since the probability of two components is 0.0121 is less than 0.05. What is the probability that a parallel structure with two identical components will succeed? Well, you can do that two ways. You could either take 0.0121 away from 1, or you could multiply 0.89 to the second power. So what? 9879? Is that what that is? 0.9?
Yes, sir.
I don't know. I'll take it away. Let's do it here. 1 minus second answer should be 0.9879. Is that what I said? Said round to 9879. Now, how did I do that? Well, what is the probability of two failing? I just told you that right here. This is the probability of two components failing.
Are you writing something?
So if two components is failing is 0.11 is 0.0121, then what is the probability of two components succeeding? I don't know how to spell succeeding, but words got too many letters in it. Okay, now I want to ask you a question. If two components is 0.0121, then what is the probability probability of two components succeeding? 1 minus 0.0121. And that's equal to what I say, 0.9879.
Hubert,
Yes.
I think your screen is like a little laggy because we can't really see anything.
Okay, well, I'm going to shut off my video, see if that helps.
Miss Dennis has a question.
Who?
Miss Dennis.
Yes, Miss Dennis.
I was gonna say, I don't see anything.
Well, you see something now?
Yes.
Okay, that's what we've done so far, A and B. Okay, let's see what C says. How many components would be needed in the structure so that the probability of the system will succeed is greater than 0.9998? Well, how do you find out if, how did we find out the two components succeed? Well, hold on, I'm going to do this with you on this page. I'm going to ask y'all to follow along with me. What is the probability of one component succeeding? Go back to the question. Or go back to here. Go back to here.
0.89.
I'm sorry, what?
0.89.
Exactly. We did that at the beginning of the question. You get the complement. So what is the probability of 1? 0.89. Somebody give me the probability of 2 succeeding. That would be 0.89 to the what?
Second power?
Good job. And that would be what we just got, but I'll do it anyway, because I'm trying to help y'all out as much as possible. So 0.89 raised to the second power. 0.7921. What to the third power? 0.89 what? To the third power. You'll see this in just a minute. Second entry. Change that to the third. 0.7049. Should be going higher. 0.7049. Or I'm going the wrong way. Second entry to the fourth power. Yeah, it's going the wrong way, so we're going the wrong way. Probability of 4 succeeding. We're going to have to go the complement. We're going to have to go backwards. So the fourth is equal to 0.6274. The way that you do C is you do it trial and error. You do it until you get above 0.98.
Facebook comment.
0.9. So we're going to have to do the complement. All right. So we're going to have to do 1 minus 0.11 to the third power. 1 minus, let's see, we've got 1 minus 0.11 to the second power. Let me do that again in the calculator. I told y'all this wasn't a test question. 0.11 to the second power. And 1 minus 0.11 to the third power. There we go. 1 minus 0.11 to the fourth power. And what was our number that we had to get above?
I believe it was
What does it
0.9999.
say?
Is it 4 nines?
0.9998. .9998 here, so 3. That's 0.999 right there. So to the third, so 3 components. So how many? 3. Well, that's what I got. That's what we just did. Maybe they want 4 then, because 4 is higher. Yeah, they wanted 4. Let's look back and see. Look back at our calculator. 0.9998. Oh, is that what they wanted? 3 nines? Oh, I'm sorry. 3 nines. I read it wrong. I read 2 nines. So look at your calculator. That's 2 nines. I got that wrong. It's 0.9998. So it was 4. And that's what goes there. The 4 components. So it would take 4 components failing. Or this is 1 minus, this is succeeding. So that's how you would do that. So what I would get you to do is, hold on a second. Get back to here. This is failing. And this is succeeding. 1 minus 0.11, we said that was point what? 0.9879. And 1 minus 0.11 to the third power is equal to 0.9986, 0.998669. And 1 minus 0.11 to the fourth power is 0.99985359. And that's the one that is at 0.9998. So this is the one. So it's 4 components. I'm not asking that you understand these questions. I'm just showing you how to get through them, because these questions are a little bit on the confusing side. But let's do another one. Let's do a similar question. All right, do this one.
Over 5.5.
Yeah, I'm gonna try to. Let me finish this last question. Thank you for reminding me. All right, so this is, what is that? The probability of failure. The probability of failure is equal to 0.26, right? Therefore, what's the probability of success? Somebody give me the probability of success.
That would be, sorry, I'm just looking at it. That's 100 just minus 26, so 74. Or 0.74, excuse me.
1 minus 0.26 is 0.74. That's the complement. All right, so the first thing they say is, would it be unusual to observe one component fail? A, one component is 0.26. Is 0.26 greater than 0.05?
Yes.
Yes. So since that is a yes, that means it's normal, because it drops over into the green area, or not unusual. Now let's do 2.
Are you sick, Hubert?
No, I'm fine. I just had to clear my throat. Well, no, I just
No
overslept
clearing
this
throat in
morning.
class. You can't clear your throat in class, Hubert.
Oh, I'm
You'll
sorry.
get thrown out.
Okay, I'm sorry. 0.26 to the second power is blank to 0.05. Somebody tell me what 0.26 to the second power is.
I got 0.0676.
And that's greater than what? 0.05. Therefore, it's normal and not unusual. So this one, we got 2 that are normal. So you go to your handy dandy question and you say it is not unusual. It would not be unusual because 0.26 is what? Greater than 0.05. It would not be unusual for 2 because 0.067 0679 or whatever you said is greater than 0.05. I probably typed that one in wrong.
I believe it's 0.0676.
Thank you. There we go. What is the probability that a parallel structure with 2 identical components will succeed? Well, that will be 1 minus 0.067. Go ahead and subtract that one. B would be 1 minus 0.0676. That would be 0.9324. Somebody
Yes,
check
sir.
me. What?
Yes, sir. That's right.
Okay, now we're going to start running our trial and error. So I'm going to do it with you on the whiteboard here. I don't know. What do they want? 0.9999. So we said that 1 minus point, this is 2. So 3 would be B, or I'm sorry, 3 components would be 1 minus 0.26 raised to the 3rd power. So let's do that in the calculator. Clear. 1 minus 0.26 raised to the 3rd power is 0.9824. And 1, I'm going to hit second entry, raise it to the 4th power. 0.99, 1 minus 0.26 to the 4th power is 0.99543024. That's 4 components. 5 components would be second enter. 5 components would be 0.91 minus 0.26 to the 5th power is 0.998811824. 6 components, second enter, 6, 0.99969, 1 minus 0.26 to the 6th power is equal to 0.99969. So it's probably going to be to the 7th. Second enter, 7th. There she is. 7 will be 1 minus 0.26 to the 7th power, which is equal to 0.9999 and 19. So they wanted to know how many components would it take to get to 0.9999, and the answer is what? 7. And you feel good about yourself.
Hubert, I have a quick question about the homework.
Yes.
So I was looking on MyLabs Plus, and it says that you assigned a due date for the homework questions due today.
For what sections?
4.1, 4.2, 5.1, 5.2, and 5.3.
Well, I might back up on 5.3, but the 5.1, 4.1, 4.2, 5.1, and 5.2, they should already be done. Okay, but I'll open the other ones. Yes.
I had trouble with 4.2, and I sent you a whole bunch of questions.
Okay, well, we'll go over them. I'll open it back up, but I can't go over, I can't go over a lot of questions in 1 hour, so I'll have to break it up and go over some more questions. I'll have to open it up, the questions on, let me go through 5.5 and then I'll open up the homework, okay?
Okay.
Sorry about that. So 5.5. Here is 5.5 material. 5.5 deals with counting. Now, what does counting mean? Well, counting, 5.5, basically is with factorial. Okay? Counting means multiplication, exponents, and factorial. Now, y'all know about multiplying and exponents. Here's one. If I give you a choice of salad or soup for an appetizer and 4 entrees, let's go with fish, chicken, red meat, and tofu. And then I say, and of course, the vegetables come with all those. You don't have a choice with that. Okay. And cheesecake or ice cream. And this is a test question, so you might want to write it down. How many different combos can we get?
A lot.
And how many entrees are here? That's 2. How many entrees are here?
4,
That's 4. And how many are here?
2,
And you multiply all 4 of those. 2 times 4 times 2 is equal to 16. Now that is multiplication. All right? That is multiplication. So that is an example of a question in 5.5 dealing with multiplication. Now, how did you know, which one to use? Well, it depends on the question. All right, this one is just straightforward. You got 2 entrees, you got 4 entrees, you got 2 entrees. What's the total number of combos? And there it is. All right, so that's multiplication. So most of y'all, when it comes to multiplying, everybody can pretty much multiply because you all went through a placement test to get into 120, and one of those things that you have to master is multiplication. Boom. Here's the second type question you might have for exponents, or here's some questions that you might have for exponents. The word smile. How many different arrangements can I arrange those letters in the word smile? Oh no, that's not the one I need. No, forget that. We're not doing that one yet. Let's do a license plate and an alarm code and a PIN number.
Gmail.
Alarm code, let's do 5. 1, 2, 3, 4, 5. And PIN number 1, 2, 3, 4. And a license plate 1, 2, 3, 4, 5, 6. Now, this is a license plate, this is alarm code, and this is a PIN. Whenever you're dealing with these types of questions, you're going to be using exponents. Okay? The exponent will always be the number of spaces. How many spaces do I have here? 6. How many do I have here? 5. How many do I have here? 4. So that's the exponents for my each situation. Well, what are the spaces? I'm sorry. What goes in the spaces? Well, there's only 2 things normally that go into spaces. Somebody tell me what they are.
Numbers and letters.
Numbers and letters. Numbers and letters. Numbers from 0 to 9, which is equal to 10. Letters, A to what?
Z,
A to Z. And how many is that?
26.
So if the exponents is your spaces, then what are these 2 numbers going to be depending on your directions? These are going to be your base. So let's say that all 3 of these are numbers. In other words, you got a license plate with 6 numbers, you got an alarm code with 5 numbers, and you got a PIN number for 4 numbers. Everybody with me? Then this one would be 10 to the 6th. This would be 10 to the 5th, and this would be 10 to the 4th. And let's take our handy dandy calculator out. 10 to the 6th. So that'd be 1 million. 10 to the 6th is 1 million. So this one, we have 1 million different combinations, or 1 million license plates. Second entry, change that to a 5. How many different alarm codes can we make? 100,000. And how many different PIN numbers? Second, change that to a 4. And there are 10,000 PIN codes that we can use. All right, so that is, I'm going to show you another one here on the next page. License plate with 6 numbers, 1 million different license plates. An alarm code with 5 numbers, 100,000 combinations. A PIN number with 4 numbers is 10,000 combinations.
Quick question.
Yes.
So is that saying that those are all the different combinations for numbers?
Yes.
Okay.
For those 6, yes.
Thank you.
Okay. Now, what if I gave you the following license plate? Here's the license plate. You got 6 spaces. These 3 spaces, letters. These 3 spaces, numbers. Tell me how many different combinations you can have. Go ahead and take a minute and work on that.
9 and 9.
Well, this would be 26 to the 3rd power times.
10 to the 3rd power.
Good job. So let's go ahead and take our calculator. I need 26 to the 3rd power times 10 to the 3rd power. 17,576,000 license plates. Now, why did that go much higher than our 1 million? Because we added what? We added letters to it. That's a test question right there.
Can you do that on your calculator? Let me see what buttons you hit.
Trying to get there. Hold on. There they are.
26.
26 to the third power times 10 to the third power. Clear. I'll do it again for you. 26 to the third power times 10 to the third power. Now, that is a test question as well as a standardized test question. Because most license plates have what? Letters and numbers.
Oh.
Okay? All right, what else can we do? Now, that's your exponents. What is factorial? Factorial is basically multiplying numbers in their natural sequence to 1. So 3 factorial would be 3 times 2 times 1, which is 6. 4 factorial, 4 times 3 times 2 times 1 is 4 times 6, which is 24. 5 factorial, 5 times 4 times 3 times 2 times 1 is 5 times 24, which is what? 120?
Yes, sir.
Y'all check my math. You can do this in your calculator also. Now watch what I do here. I'm going to clear everything so that way you can see what I type in. Three, math, probability, and I want you to make a note, number 2, number 3, and number 4. We're going to be using those in 5.5. Number 2, number 3, and number 4. In this case, it'll be number 4, factorial. And hit enter, you get 6.
You have a work
Let's do
email.
5 factorial. 5, math, probability, factorial. Enter. Now let's do 13 factorial. Thirteen factorial. 13, math, probability, factorial. And that's a big number. Let's see, 800, 6,227,000,000, 20,800. Now, when do you use factorial? Got 3 minutes, so I'm going as fast as I can. Okay, when do you use factorial? You use factorial when you're dealing with arrangements, combinations, and permutations. Arrangements, combinations, and permutations. Smile. How many different arrangements of letters can you do with the word smile? Well, that would be 5 factorial, which we said is 120. So there's 120 different arrangements of the letters smile and smile. Okay, you could make one. Now, I didn't say they mean anything. You could make one miles, M-I-L-E-S. See, that's an arrangement. But some of them don't mean anything. Some of them are just an arrangement. A combination. Combination, I'm going to put under combination, no order. Permutation means order. Permutation, combination is going to be written like this. N-C-R. That's a combination. 5, combination 3. So let's do 5, combination 3. Calculator. Clear. And clear. 5, math, probability, combination, 3. 10. Permutation is N-P-R. I'm going to do 10, permutation, 3. In your calculator. 10, let me clear everything. Clear, clear, clear. This will be on the video. 10, math, probability, permutation, 3. 720. Okay, now we're going to shut her down right here. I will open up the homework for another day or two, and I'll just leave it open because I want to finish with 5.5 Wednesday. So we'll finish with 5.5 Wednesday. I need you to read 5.5 and don't do any problems. I want you to read 5.5 and go ahead and keep working on the other homework, and I'll extend it and everybody can work on it, okay?
Sounds good.
Did anybody come in after I called the roll? Don't leave yet,
I believe I
especially if you came in late.
Brenda.
Hold on.
I came in at about 11:20.
Hold on a second.
So.
Bash and Jacob. Jacob came in. Got you, Jacob. You can leave. Dennis came in.
Mm-hmm.
Garcia. Did Garcia? Nope, she didn't come in.
Yes, Garcia.
Hoopa. She didn't come in.
Garcia's on.
Well, she's not on my enrollment here.
Vienna Garcia.
Miss Garcia, are you here? Miss Garcia's not here. McLean, did Miss McLean show up? No. Owens, did Owens show up? No. And Simmons, Williams, Winton, Wright, Yoakum, all of those. Let me look at, I don't think any of those showed up. All right, y'all have a good one, and I'll go open up the homework right now, okay?
Thank you.
See y'all.
Have a good week.
What?
Hubert, can I talk
What?
with you real quick after everyone leaves?
Yeah.